Any questions before we begin? Okay, so let me just explain what we were doing at the end of yesterday's class and what the idea of the matrix is. Um, so you can have a vector, right? So you can take a vector, as I said last time, vectors usually you use the letter V. For now, like the vectors, we're giving them two entries, so you can think of them as arrows that you draw on the XY plane. So this is like a vector, and the idea is that we want to use a matrix. So for us, a matrix. So something like this is what's going to be called the matrix in general. Well, in this case, a 2 by 2 matrix to be more precise. 2 by 2, I'll explain this convention later today because it has two rows and two columns, but for now it doesn't matter. Um, so here, this is going to be a matrix, and the idea is that the point of a matrix is it is like some sort of like recipe or gadget that allows you to turn a vector into a different vector. So this gets used. So it is convenient to think about it like as some sort of like a machine or process. So you can think that the input, you have like a machine. Let me make this smaller. So yeah, it's like a machine that runs from left to right. So it goes this way. You have a machine, the input that you feed to the machine is this vector xy. As I said yesterday, like usually we'll keep the convention where the vectors are written vertically. So you feed into the machine the vector xy, and you let it run through this process. The process is the matrix A, B, C, D. And what the matrix will spit out, or what this process spits out, is a new vector. So you get a new vector. But the idea, I mean, that makes sense. Like the idea is like the entries of the new vector depend on like the input that you feed to the machine and the machine itself. So the new vector depends on those two things, and the formula in which how it depends on those two things is like, let's see. Okay. So what it means here is that the first entry of the vector is going to be ax plus by, okay? And the second entry of the vector is cx plus dy, okay? And well, this new vector, you have to give it a name, and since it depends on both the matrix and the vector that you started with, this new vector gets called AV. So think of this as the name for the new vector. Is that making sense? Or are there any questions about this? I mean, I'm about to do some examples, but not sure about the setup. If this is okay. So again, a machine, like the matrix is a process or a machine that relates to different vectors. The input vector and the output vector. Okay, so let me give you some examples. This is the one that we were doing last time. Okay, so here are some examples from last time. So last time we had a vector xy, and we could rotate it by an angle, right? So imagine that I rotate it by an angle theta. So what we found last time is that there was a matrix. In this case, like usually the matrices, I'll tell you about that later, but usually the matrices for us will always be uppercase letters. Uh, the letters that you tend to use for them are like A, B, C, but in cases where like the matrix is special, you can use a different letter. So in this case, I'll call it R for rotation. Okay, so um, so that's like the matrix would rotate you would need to use to rotate the vector. And what that means is that again, if you think of this as A, B, like the minus is included in the B. So this is A, B, C, D. What that means is that the vector that is going to produce here was what? Cosine of theta minus sine of theta, sine of theta, cosine of theta, and then x, y, and if there's no sign, it's implicitly a plus. So that's why there was a plus last time. Okay, so the first entry is cosine of x minus sine of y, and the second entry is sine of theta, sorry, cosine of theta x minus sine of theta y, and the other one is sine of theta x plus cosine of theta y. Okay, so we can apply this in a specific example. So let's try to say like you want it to rotate by 90 degrees, right? So just to make this more concrete, let's say you want to do theta equals pi over 2 or 90 degrees, right? So what does like the rotation matrix become? Let's see if I give it a specific name here. Well, no. Well, what is cosine of 90? Anyone remember? Cosine of 90 degrees? What's that? So cosine of 90 was 0. Sine of 90 was 1, right? So there's a minus sign, so it becomes minus 1. Then sine of 90 or sine of pi over 2 is 1. And cosine of 90 is 0 again. So the matrix that rotates by 90 degrees is actually 0, minus 1, 1, 0. Okay. So to make this more a better picture, what that means is that if you started with the vector xy and you wanted to rotate this by 90 degrees, so the new vector now looks what it means for it to be 90 degrees, it looks like it means that it will look perpendicular to the other vector, right? Okay, so anyone wants to try to give me the entries of this new vector? It's literally just like this, like A, B, right? This is A, B, C, D, or just plug the 90 equals, you know, just plug theta equals 90 degrees in this formula for the entries of the vector, right? So what do we get? What are the entries that we get here? What's the first entry that you would get here? So what you can do is like, again, you can kind of copy the entries. It's kind of making a copy of the same entries on the vector. So the entries, like on the first row will appear in the first entry on the vector, and the entries on the second row will appear in the second entry of the vector. It said that each entry gets multiplied by the variable, so it gets multiplied by x, y, and then x, y. And so what does that give you? It gives you what? 0x, you don't need to keep track of it, so you get minus y in the first entry. And then here 1x, that's fine, and then 0y, there's no need to write it. So you get negative yx. So what that means is that maybe I should do it like, and again, with a nicer, cleaner example, cleaner picture. What that means is that if you had like a vector xy, the vector that has entries negative yx is perpendicular to that one. Is that okay? Is that making sense? Right, right. Yes, correct. So like we can make this more concrete, yes, if you want. So exactly. So what this means is that good. So if like the first vector was like 1, 2, right? The second vector, what are the entries? So it would become negative y, so it's negative 2, right? And then x, it was 1. So the horizontal coordinate or the x coordinate of this new vector is negative 2, and the vertical coordinate is 1, which are, yeah, kind of like in terms of the numbers, like they come from the previous vector, but yeah, the one that goes here is the convention is always like that's always the x coordinate. It just happens that the x coordinate of this one is the minus y coordinate of the previous one, but that's okay. Yeah.
So, Professor, we just need to remember when the angle is 90 degree. So that would be the opposite for the rotate, vectors.
Well, in this case, I mean, the 90-degree matrix is kind of the rotation by 90 degrees. I'm doing it just because it's like a very natural angle to try. In general, I'm not sure if I will ask you. I mean, I
Oh, for
may just give you this formula for the matrix. But yeah, like if I gave you like what I'm trying to say is that if once you have the formula for the matrix, right, you don't have to memorize anything else, because then you will plug in the value for the angle that you want, right? And once you have the value for the angle that you want, then you can like work out again the formula, if that makes sense. So
okay,
you don't have to remember that for the 90 degrees this was minus y and this was x,
okay,
because you can sort of work it out. But like let's like for example just to give you another one to try. Like imagine if I like again this was the rotation matrix in general, right? Um, imagine that I said, well, I don't want to rotate by 90 degrees now. I just want to rotate by 45 degrees, right? So I want to rotate a vector by 45 degrees. So what would the rotation be? Anyone remember what cosine of 45 degrees is? Yeah, you can write it that way. Yeah, so that's one way to write it. Root of 2 over 2. And cosine and sine become the same at 45 degrees, right? So this gives you minus root of 2 of 2. Then this gives you root of 2 of 2. And then this one gives you root of 2 over 2, right? So that's what the rotation looks in this case. And again, what that means is that if you do x and y, right, you can put like the vector here, x, y, and I want to find now like the vector that was rotated by 45 degrees right now. So there's going to be now like a 45-degree angle here, no longer 90 degrees. So, but it's kind of the same. The idea is like, you know, you literally just copy paste the entries of the matrix, right? So you copy paste these entries of the matrix. So like the horizontal ones go into the first entry of the vector. Sorry, the ones in the first row go into the first entry of the vector. The ones in the second row go into the second entry of the vector. That's easy to remember. And then you put x, y, x, y, x, y. Sorry, x, y, x, y. So you get this. And that's literally, it looks a little bit more complicated, but literally that's I mean, you could factorize a root of 2 over 2 because it's on every entry. So it is x minus y. Okay. So the first entry of the vector is root of 2 over 2 times x minus y. And the second entry of the vector is root of 2 over 2 times x plus y. But I wouldn't expect you know what I mean? I wouldn't expect anyone to memorize this formula. It's more something that you get out of by plugging in theta equals pi over 4. Is that making sense?
Yeah.
So I can show you that then in animation. Just give me 1 second, sorry. So just to show you how this looks, let me go to GeoGebra. It's kind of nice to see like an actual, like a very concrete like animation where this is working out. So let's go to GeoGebra here. So by the way, you can download it for free, GeoGebra. If you want to have the app, you can also go, if you go to their website, geogebra.com or .org, you can like work like with an online version, so that doesn't require download. But I find it very convenient. So okay, so I don't know if you see, do you see the A and B sliders on the animation? So this is going to work as the first entry and second entries of the vector. Okay, so the first vector was AV, so you get this one, right? Because the values for A and B were 1, but you see, like if I change the value for A, that's changing the S coordinate, right? Can you see here? And if I change the value for B, that's like changing the Y coordinate. Okay, so you have the sliders. And then like the new vector, I mean, we could call it U or whatever. If you remember, if you look at the formula that I wrote, it's square root of 2 over 2, right, times x minus y, but x minus y here is a minus b because of the names that I had to give to the variables. And then you get square root of 2 over 2 times a plus b. Is that making sense? Okay, and the animation already called it U, so that's fine. Is that okay? And you kind of hopefully see that they are somewhat like of a 45-degree, you know, between the two of them, right? So, and then if you want, you can like do like an animation, so that you see they're always like, you can animate both at the same time. So you see they always preserve like the 45-degree angle between them. Does that make sense? So the formula, it works the way it's supposed to work. And then for the one that we had done originally, right, which was, let me stop this animation because they're kind of annoying now. Okay, and the one for the one that we had done originally, which was the 90-degree angle, the first entry had to be negative y, right? So negative y would be negative b, and the second entry would have to be x, which would be a. Okay. Okay, so now you see it's negative y, so it's minus minus the second entry of the previous vector, and then the second entry of this one is the same as the first entry of the other. And then you can still animate them. And you get that. Is that okay? But now it's at a 90-degree angle. And the idea of like the rotation matrix is that for any angle of rotation that you had wanted, you can do the same thing, basically. Is that making sense? Are there any questions about this? Yeah, it's in the. I think I sent an announcement yesterday that mentioned the section of the book where this is in. If you check the announcement, let's see. Mm, yeah, the rotation matrix. Yeah, the rotation matrix. It just they do it a little bit late, but it's on page 47, 48. Yeah, you can just use that one if you want. Yeah. That one has more colors, I guess, so it's nicer. Yeah, you can always you just have to compare with the announcement to see what it corresponds to, like which class corresponds to what part of the book. But yeah, you can do that if you prefer. Okay. Now this can also become slightly more interesting. Usually what we want to do sometimes is like in this problem, for the rotations, like we kind of had a vector. I gave you an angle of rotation, and you wanted to find the new vector, right? So kind of like the new vector was unknown. What can happen sometimes is that you have a vector. You know what you want the new vector to be, and you want to find the matrix that will give you that. So this may sound a little bit too weird. So let me give you like another example. Let's call this the mirror. Let's talk about like the mirror matrix if you want. You could also call it reflections, but let's call it mirror or reflection matrix. So in this case, it is like I have a vector x, y, okay? And I want to produce, I know what I want the new vector to be. So you want, like, imagine that now the x-axis is kind of like a mirror. So like I put like a mirror along the x-axis, right? So when you have a mirror, you just reflect the image, right? So the reflection, let's put it like here. And again, I'll call this the M for mirror. So M here stands for mirror, M for mirror. So anyone can think about what can anyone think about what the entry should be of the mirror vector? What should be the first entry of the mirror image? Yeah, it's not affecting the X entry, the X coordinate. Good. And then what do you think the entry for the second one should be? Yeah, it just flips the second coordinate, right? Good, good. Perfect. So is that making sense? So like if you have a vector, its mirror, if you place a mirror on the x-axis, along the x-axis, it makes sense that it would be the vector with entries x and minus y. So this is like a situation where we already know what the answer should be, right? We already want the answer to be x negative y. But so now the question, right, is kind of like and it's kind of like you like these engineering problems. It's kind of like the input, the output, and now you're trying to figure out what's the machine that turns the input into the output. So the question is, can you find question? So I don't know what the matrix should be in this case. So let's just call it A, B, C, D. I'm going to call it M for mirror. That kind of makes sense. But can you think about what coefficients or what numbers you should enter here? So what are the values of A, B, C, D that would turn this vector into this vector? So what should A, B, C, D be? To start with X, Y and produce X negative Y. So, okay, I mean, by that, you just have to look to figure that out. You should look at this formula that I had given in general. The numbers can be any number that you want. So try to think that out, and let me just give you 2 or 3 minutes for you to work it out. If not, we can discuss it. So I'll come in 2 or 3 minutes to see what you found. Uh, okay. So how did it go? Was anyone able to find out the formula for the coefficients? Oh my God. Sorry. I think I spoke, but it wasn't recorded. Was anyone able to find the formula for the coefficients? So let's think about that. Right, so this is a vector that I want to end up with, right? What I'm saying is that this vector you can write as how, in which way? You can write it as 1x, right? Um, there's no y, right? So let me put plus 0y. And then there's no x in the second entry, so let's put 0x minus 1y. Is that making sense?
Yes.
So based on that, what do you think the entries of the matrix should be? They should be 1, 0, 0, -1. Is that reasonable? So because again, like the coefficients of the end, the numbers that go inside the matrix are literally just the numbers that are multiplying the variables in the formula for the vector. So that's what you should find out. So in a more diagrammatic way, what this is saying, what I'm trying to say is that if you started with the vector, maybe to emphasize this, if you started with the vector xy and you run it through the machine M, which is 1, 0, 0, -1, the output that it's going to produce is this mirror vector, which is x -y, which is what I'm calling mirror vector. It's just that the mirror vector, the idea the other way in which it will be written is as, and this way which is written is to suggest that it's some sort of matrix multiplication. It is also written as M times V. Okay, so like one of the goals for the course is to just get used to the idea of thinking that you can kind of do like a multiplication between the matrix and the vector to get the new vector. So this is kind of how it would get written out, or how we will write it in subsequent classes. Is that making sense? Are there any questions about this?
Professor, I have a question. So,
Mhm.
if the vector equal to xy, and then the maybe the rotor vectors or mirror vectors equal to negative x and y, that is the actually it's the rotated or mirrored.
Oh, you're asking me like if instead of
Yeah.
of having here
Yeah, if the
x,
vectors equal to
right,
xy, and then
if
another one
right, if
equal
you said minus xy, that's the one that you want.
yeah, I mean another example that
Right.
is kind
So
of the same
we
thing.
can do it actually. So good. Right. So you want it just to make sure, like, if I get it correctly. So you want to start here with xy, right?
Mhm.
And you want to end up with minus xy, right? Something like
Yes.
that. Okay, good. So we can, okay, it's fun to get used to doing this. It is literally just reading off the coefficients, right? That are
Mm.
multiplying the variables. So like the only thing that you have to get used to is kind of rewriting this in a convenient way. So I can rewrite the entries as minus 1x plus 0y, right? Because there's no y on the top. And then I can write it as 0x plus 1y. Is that making sense?
Oh yeah. Oh, it's also
And
the method as well.
well, it's a slightly different matrix. I mean, it will be a new matrix, not the same as the older one because the minus is in the first entry instead of the second entry, right? So the matrix in this case, I mean, you could call it mirror two, or like you could call it like a different letter, like to not confuse it. You can call it N if you want.
Okay.
It would be minus 1, 0, 0, 1. Is that making sense?
Yeah. Thank you.
It's very, I mean, it is related to the other. I mean, it's not completely different from the other one because they just differ by, switching the signs along what we will call the diagonal. But yeah, you can think of it. This one would correspond to having placed a mirror along the x-axis. Sorry, along the y-axis. You see, if you had like the mirror along the y-axis, this is how you would get this one. Uh, But okay, let's do one more before again doing like a slightly switch of topics, but let's no, let's do two more. Here's one that you could also be interested in, which you could call the average matrix. Or averaging matrix. I don't know how you want to call this one, but what I want this one to do, okay? What I want this one to do is to start with xy, right? And the name here is to suggest an average. Anyone remembers the formula? What's the average of two numbers? What are the entries for the average of two numbers? Right, so if one number is 3 and the other is 5, what's their average? You do this all the time when computing grades, right? So it's just like 3 plus 5 over 2, right? So here it would be x plus y over 2. And I want that to just record both. I mean, I just want it to duplicate the average. So it's going to replace each entry with the average of the entries. Is that making sense? Okay. And I mean, it kind of, again, I'll say about that in a second, but so I give you, okay, I started with the vector has entries x, y. I want a new vector that is just the average of the entries of that or the vector. So I could ask you now, what's the matrix, right? What's the matrix that gets you from the starting vector to the new vector? What should the entries of this vector matrix be? What do you think? It's kind of there will all be the same if you want a small hint. All the entries are the same number. What should that number be? Well, it's actually right. It is 1/2. It is 1/2 on all of them. Because every variable is multiplied by 1/2, right? So yes, so it's 1/2, 1/2, 1/2, 1/2. Is that making sense? Because it's also x times 1/2, y times 1/2, x times 1/2, and y times 1/2, right? So you can write it, if you prefer, you can write this out as x half plus y half and x half plus y half. Is that making sense? So you see, like the coefficient 1/2 is in front of all the variables. But you see, like, I mean, this is like obviously a very small example, but maybe you can imagine, like when if you had like more data points or more measurements, you want to take the average of them and then store that into like some sort of vector, and then using this averaging matrix, that's one way to do it. So I'm just saying, like, the vectors, the matrices are useful because they produce like interesting vectors out of ones that you knew before. That's what makes the matrix is nice. I mean, a powerful tool. Here is here's another one before moving to a different topic. Another simple one, but it's kind of cute to have around. So let's talk about this one as the shift matrix. So it starts with a vector v. And what the shift matrix is going to do is kind of changes your mind about which entry is what. So the Y value becomes the X value, and the X value becomes a Y value. Okay, so it just kind of like, just to give you an example, if this had been the vector 3, 5, if you run it through this machine, you get the vector 5, 3. Okay, so the shift matrix will be in charge of doing that. It just changes your mind about, you know, it shifts the first with the second entry. So again, like I'm claiming that there's a matrix involved in this process. Can anyone see the entries of this matrix? Correct, good. So here's one way to think about it. Perfect, good. Here's y-x, write it just as 0x plus 1y and 1x plus 0y. And from there, it's easy to extract the matrix as 0, 1, 1, 0. Is that making sense? Good. So like, again, this is kind of like more to give you an idea that like the matrices are doing concrete things on vectors. So sometimes they rotate them, sometimes they will reflect them, sometimes they will shift them in this way, sometimes they will average them out. I mean, sometimes they will do like other things for which we have no specific names, right? But like the idea is that you should really think of a matrix as turning vectors into new vectors, like it is kind of like a process, okay? And so now after, like in a moment, I'll do like a mini break because it's a good place to switch topics. But like the goal is going to be like, well, think about it like as a factory, right? One, you have different machines, you have the rotation machine, the shift machine, the reflection machine, you know, like a bunch of different units in your factory. And what you can do with machines? Well, you can concatenate them, right? Like, you know, doing first one machine and then the other, or like so, or you could try to combine it in different ways. So what we're going to talk about next, after this mini break, will be how you can start with matrices and produce new matrices out of them. Okay, and that
Yes, sir.
would.
A quick question. So for the 3, 5 to the 5, 3, the
Yes.
S supposed to be S equal to 5, 0, 5 and 3, 0, right?
Oh, you have to be careful because these here is, oh, this is like X and this is like Y, right?
Yeah.
So it's still 1 times 5, you see? Because yeah, that's a good question. So if you have 5, 3, right? It is 1 times 5 plus 0 times 3, right? And then what is like it is very confusing if you actually try to find it in terms of the numbers. That's why it's better to write them with variables first, because then like it is like, I mean, you can kind of still see it from here, but it is like kind of weird to see it that way, you know what I mean? Yeah, sorry, actually I should write it like yeah, you can like, you know, I already got confused like trying to write it this way because it's not it just looks a little bit odd to put it this way. You know what I mean? So you cannot really read out the matrix too well if you have specific numbers in the
Mm.
you have to kind of have them in terms of x and y. If you have them in terms of x and y, it's kind of unambiguous, but if you just have them as numbers, it's not so clear. Is that making sense?
Yeah, it makes sense. Yeah.
Yeah.
Thank you so much.
Sure. Yeah, no, so we still have to talk about that product at some point. I'm not sure if today or tomorrow, probably. There is yeah, the thing is like these operations can be seen as some sort of dot product, but well, we'll get to that shortly, depending on how much I mean by shortly, but not right now, at least maybe in a couple of minutes. So okay, yeah, so as I was saying, like now you have some acquaintance with this matrix stuff. So let's take a 5-minute break, and when we return, I'll tell you other things you can do with matrices, like more among matrices themselves. Yeah, and we can discuss other things after that. So, but yeah, let's just take a 5-minute break. And when we return, we'll talk about that. Okay. Let me continue. So, what we have to talk about now, is certain operations that you can do among matrices themselves. So again, kind of two will be very easy, and one will be relatively confusing, and that's kind of what makes linear algebra interesting, the third operation between matrices. But we can start with the easy ones first. So the first one is just multiplying a matrix by a number. By the way, I don't think I said it yesterday, but there's like a terminology convention, which I don't want to make a big deal out of it, but I may, you may see it on the books. You know, instead of saying number, it's common in the linear algebra textbooks to call a number a scalar. So like just as a remark, numbers sometimes called scalars in linear algebra. So instead of saying like 3 is a number, they would say like the scalar 3. I mean, it's not like, I'll probably just stick to calling them numbers, or I'll just use the both names simultaneously, just so that it's, you know, to emphasize that they're really the same, but they don't, you know, it's like sounds a lot more intimidating than what it actually is. So but okay, but anyway, so what I'm saying is that if you have a matrix and you have a number, there's a way to kind of multiply both of them. So like for example, it is so straightforward that like a couple of examples like should clarify it. So if I had the matrix with entries A, B, C, D, right? And I wanted to talk about the matrix 3A. So again, think about this as a number 3 times the matrix A. Okay, that convention, or like what ends up being most useful, is to just multiply every single entry of the matrix by that number. So you just put like a 3 in front of everything. I mean, that again ends up being the best, like the most natural thing you could do. So like if the matrix had been like, you know, I don't know, 1, 2, -1, 3, like the matrix 3A would be what, like 3, 6 minus 3, 9. Is that making sense? Again, like it's like if you knew nothing about matrices, like if you just saw like those arrays of numbers, like if you just had to make a guess, that's probably what like you would have gone with. Like so there's nothing like really magical, mystical going there. It is kind of like the like analog of the vector. You know, if you had like a vector, you could multiply it by a number. We did that yesterday. And if you remember, every single entry of the vector got multiplied by that number. So it's kind of like doing the same, but for the matrix case. Okay. So again, yeah, the rule is to multiply every single entry of the matrix by that number. So you multiply every entry of the matrix by that number. Okay. So again, we're kind of following the analogy between the vector case. So with vectors, we multiply a vector by a number, and then the next thing we did was adding two vectors, right? So there is a way to add matrices together. Okay, so let's call that operation 2. Which is adding matrices. So again, you kind of just end up doing the most natural thing, which is just to add the corresponding entries of the matrix. So for example, if A is like A, B, C, D, and B is like what, E, F, G, H, like if you had two matrices like that, what you want the matrix addition to be is just like the matrix that you would get by, you know, like adding them together, adding the entries together. So again, like you could make this concrete if you wanted to, although hopefully it's not too, it doesn't seem too confusing. And let's see. If you have two matrices which look like that, then A plus B is literally what you get by doing the corresponding sums. So 1 plus 4 is 5, 2 plus 5 is 7, -1 plus 0 is -1, and 3 plus 3 is 6. So hopefully I didn't get any of them incorrect. Is that making sense? Okay, so adding matrices and multiplying matrices by a number, that's relatively easy. Now, the one that significantly more complicated is what we could call like concatenation of matrices, okay? Also called matrix multiplication. If you think about it as an electric circuit, that would be the analog of putting like them in series. If you think about like, you know, like the matrix as some sort of machine or like a resistance, a resistor, what is it called? And then you put them in series, so. So what do I mean by this? Let's do it. Let's start with something concrete. So we'll have two matrices in this for this example, just to begin with. So we'll have the mirror matrix, which we had seen before, just to make it simple. Right, the mirror matrix was the one that started with x, y, and took its mirror. So the mirror gave you what, x negative y, right? That's what the mirror matrix would do. And I want a different color for the shift matrix. The one should also be fine. So we also had the shift matrix. Which was 0, 1, 1, 0. Which would start with the vector xy. And if you remember what the shift does is like just shift the entries, right? So 2 becomes 1 and 1 becomes 2. So yx. Okay, so you have these two machines, right? You have these two processes. Okay, and the idea, in as of now, they're kind of like, if you thought about it, like you know, pictorially in a factory, it is like this machine is on one side of the room and this other machine is in the other side of the room. They're not like, interacting with one another. But if you thought about it as a factory, like a production line, you could just do like, you could start with an input and apply one machine first, get that output and feed that into the second machine as the input. Is that making sense? So let's try to like see if what I'm saying is kind of reasonable. So what I'm saying like is that you could do something like mirror then shift. Okay, let's do mirror then shift. So what I mean by that is that I'm going to start with a vector x, y. And I'm going to feed it into the mirror machine first. Okay, and it spits out the vector x negative y. Right, that's what we just did before. But now the difference is that I'm going to use that and use this one as the input for the second one. Okay, so I'm going, instead of just feeding it x, y again into the shift machine, I'm just going to take this one literally and place it here. So this is the one that's going to be fed into the shift machine. Do you see the difference? So it's kind of like a refined product that we're feeding into the shift machine. Is that making sense? But the shift machine still does what it's supposed to be because it's a shift machine. So it is supposed to shift the entries, right? So what should be the first entry here? Yeah, exactly. That's the point. Because the shift literally what it did was kind of move them on an X. So you're just supposed to continue doing that. So you get negative Y, and then the second entry should be X. Because like the shift is still acting as the shift machine, right? It's just you gave it a different input. Yeah, excellent observation. Not that you had to realize it, but it just happens in this case that if you do a mirror and then shift it, it is equivalent to having rotated that by 90 degrees. Yes. But it's not something that I wanted you to not kind of notice. But yeah, the important thing is like more like to at this moment like understand that there was you know there is like this we're kind of putting the stacking the machines one after the other, so it's really like a production line, right? But yes, like what I want to say is that you could think of like someone, you know, could think about building a single machine that starts here and gives you this, right? Kind of like combines, like, you know, paste together these two tubes, make them into a single like machine, bigger machine, which we could call the mirror then shift machine. So let's call it like so let's call this one the mirror then shift. So the mirror then shift machine literally starts with XY and gives you minus YX. And this one, if you think about it, just you can extract the machine from the formula, right? From the coefficients. It gives you what 0, -1, 1, 0, right? Because those are like the coefficients like that are appearing here. The fact that it happens to coincide with the rotation by the 90 degrees is like a very nice like well, not a coincidence. It's a nice fact, but it's not something too important here. It's more like the fact that the two processes can be combined into a single process. Is that making sense? Are there any questions about this so far, so good?
Professor, could you explain one more time, like the process?
This one, you mean?
Yeah.
So you start with a vector xy, right?
Mm.
You look at its mirror, right? The mirror, if you remember, it was just like changing the
Yeah.
sign in the second entry. So that's why you get that, right?
Yes.
And that, what I'm saying is that think of that feeding that into the second machine, right?
Mm.
The second machine, what it did was just shift the entry. So like the second entry became the first one and the first entry became the second one, right?
Okay.
So that's why it's kind of like literally thinking about, yeah, you're doing two things to the vector. First, like you're reflecting it, right? Or looking at its mirror, and then you're shifting the entries. So I'm saying like that two processes come one after the other is what I'm representing in this diagram. Is that making sense?
Yeah, but how did you get a mixed rate at the bottom?
How did I get? Oh, okay. And then what I'm saying is that someone could think, well, let's try to kind of, you know, create like a single machine that represents this process, right? Of starting with
Yes.
XY
Yeah.
and ending with minus YX. How do you get that? You have to do the same trick as always, where if you have minus YX, that's the same as 0x minus 1Y, and then 1x plus 0Y.
Okay. Gotcha.
And then that's how you get that's how you get these coefficients. Is that making sense?
Thank you.
No, good. Perfect. Okay. So now comes the next question, right? Which is, okay, what is a question you could ask now? Like, I mean, this maybe it's a little bit unfair, but what's like, so I'm showing you what happens if you do the mirror and then the shift, right? What's another thing you could wonder about? Well, I think you could think of is what happens if you shift and then mirror, right? So you could put them backwards, right? Again, the opposite order. So it is something that we have to check what it gives us. The important thing is to realize that that's in principle a different process, right? It could end up coinciding with the ordinary one, but there's no reason why they have to necessarily be the same. That's what we have to find out. So again, the shift machine, now you're using that one first, right? So in the shift machine, you're using this one first. So that shifts the entries of the vectors. So the entries become y, x, right? And now that's the one that you are going to feed into the mirror machine. And what should you get in this case? What should have, what is the first entry I should put here?
Y and negative X.
Perfect, yes, excellent, good. Because the mirror is supposed to change the sign of the second entry. So it's still doing that. Is that making sense? So first, like an important thing to notice, notice that you ended up with something that's not really the same as was like the end result of the when you do it in the opposite order, right? So because here, like when you do mirror shift, you get minus y x, but when you do shift and the mirror, you get y minus x. So you're not getting the same output at the end of the two, right? So that's important to notice that the order matters. And let me just also emphasize this with a diagram. So you could have like a single machine that represents these two together, right? So you have x, y here, and then you have y minus x here, right? So what I'm saying is that this can be represented by a single machine, which we can call shift the mirror. And that that matrix is like the matrix what?
0, 1, and negative 1, 0.
Perfect, yeah, because of the same trick as usual. Like I should write it just in case that 0x plus 1y, and then minus 1x plus 0y, right? But if you see the matrix, this matrix is really different from, I mean, it's not too different, right? Okay, you could kind of like try to relate them, but like the important thing that I'm trying to make here, like what I'm trying to emphasize at this point is that they're not necessarily the same matrix. How much they differ is like other question you could ask, but it is not the same matrix, right? And, so maybe I should stop up to this point. Like, is that making sense so far so good? Any questions up to this point? The important thing is that when you have two matrices or two processes and you put one after the other, the order does matter. I mean, and that's kind of what happens in real life most of the time, right? If you have like a factory, like an actual factory, like, you know, a product that's being refined in a production line, you would probably care about like the order in which the refinement is going, right? So in most things in life, like order matters. So I'm just saying in this particular case, with the matrices, this concatenation thing is sensitive to in which order you do them. So this example was just to explain that first, like it's kind of useful to see it concretely, that the order in which you're doing this matters. So the moral of the story is that the order when concatenating matrices matter. Okay, and then since the order matters, it just means what I'm going to do now is I'm going to give you like a notation for this operation of putting one matrix after the other. It's just that that means that we have to be careful with that notation, so because it will matter in which how you're getting it. Right. So the idea exactly. What I'm going to say is that the idea is that when you have two matrices, you're going to define what's called the matrix multiplication, and the matrix multiplication corresponds to this operation of putting one matrix into the other after the other. So let me try to do it first in a diagram. But yeah, that's essentially what's happening. So like, so if you had the mirror and then the shift, right? The mirror was 1, 0, 0, -1, and then the shift, right? Which was 0, 1, 1, 0. What I'm saying is that the idea is that there's going to be an operation that I'm going to call matrix multiplication, because that's usually how it's called. So there's going to be something called the matrix multiplication that will give us this third matrix that we had talked about before, the one that represented this combined process. So I'm trying to keep the same colors. So 0, -1, 1, 0. So this new matrix, like the third, like the concatenation, or like doing mirror and then shift, that's the way in which we will write it, is that we will write it as S times M. So what this means is that I'm going to tell you in a couple of minutes probably, or yeah, I'll tell you. So like what I'm trying to say here is like we're going to define the matrix multiplication. And the result of doing that multiplication will be this concatenation matrix, this matrix that you get by concatenating the processes. Okay, but like the important thing to notice here, I mean, it will become clear because I'm about to write the diagram in the opposite order, is that in this, if I write it this way, I'm really saying that I'm doing the mirror first and then the shift, which can be confusing because that's typically how we don't write things like in English. So you kind of have to read it from right to left. Okay, so, but again, let me just maybe do the second diagram because it may be a better think to have them in contrast. So here, what I'm saying, we were doing shift and mirror, right? The matrix that we got when we did shift and mirror was 0, 1, -1, 0, right? And what I'm saying is that I'm going to define an operation called matrix multiplication, where this literally will be m times s. Okay, but you see the difference between them? Like the difference is the order in which they appear, right? So in this notation for the multiplication, this means do s first and then m, and this in this notation it means do m first and then s, which can be confusing. So the notation, you have to read it carefully, because as we just saw, it is not true that it won't be true that s times m is the same as m times s. So that's where you have to be careful about that. I still haven't given you the formula, of course, but I'm just trying to explain this out. That making is that making sense? So far, so good. So again, like the point of the matrix multiplication will be defined so that it coincides with concatenating the matrices. That's kind of how it's defined, basically. But because like concatenating the matrices, the order matters, you just have to make sure that how you write this out matters. Okay. So let me give you the formula. This is like a formula that takes a little bit to digest. So also tomorrow we'll spend some time trying to get used to it. So for today, probably would just seem like a complicated formula, but you'll see there are ways to memorize it that makes it look less weird. But probably today, because I don't want it does take a little bit of explanation, but so here, like the formula for how the matrix multiplication is going to be like. So the idea is that you started with this vector v, which is xy, and you are applying a matrix A to it. Before A was mirror matrix, but now it's not necessarily the mirror matrix. It's just a matrix that we are calling A, B, C, D. Okay. I will need some space here, so I will try to make this kind of small. Okay, and remember that when you do that, you end up with a new vector, which is literally copy these coefficients, like the coefficients in the first row and appear in the first entry, and the coefficients in the second row appear in the second entry. So you get something like this: ax plus by, dx plus dy. Okay, that's what you get after applying the first matrix. And then Now we're running this through a second matrix, right? Which I'm calling EF GH. Okay, so I'm actually doing the analog of what we had before. It's just that now I'm not giving specific numbers to the entrance of the matrix, so that's why it looks a little bit more confusing. But if you remember the formula, again, like now this is what you're feeding into the matrix, but the formula for like obtaining the new vector is the same. These coefficients go into the first row, and these coefficients go into the second row. It's just that now, remember before it was being multiplied by this coefficient was here, like this coefficient was multiplied by x, but now x is all of this. So that's what where the different lies. So you have to copy this one. I think I'll probably let me zoom in here to make it better. Because this is kind of like the new x, you see, that's the thing you have to realize. And then f was multiplied by the second entry of the vector. That's a better way to say it. It's just that now the second entry of the vector is this one. So you put like here's px plus dy. And now you do the same for the second one. Oops. Okay, I don't know if I'm gaining time here. Okay, take it back. This is not going to work. Okay. I mean, I'll write this formula a lot better in a second, but I'm just trying to explain to you what is happening. So what I'm saying is that yeah, it's like a long thing. So what I'm saying is that when you apply the first matrix, the vector that you end up getting is ax plus by and cx plus dy. Those are the entries of the output. But then this one is the input for this one. And so the output after applying that will be this mess. So you don't have like, again, I'll give you better ways to memorize the formula tomorrow. So you don't have to worry too much about going through all of these details, but it's kind of like just telling you like, if you gave like general coefficients, if you don't give specific numbers to the entries of the matrix, and you just call them A, B, C, D, and E, F, G, H, that's what you would end up with, okay? It's just that it is a bit of a mess, and it's not like a useful way to write it. So let me let's just work this out a little bit better. And from there, you'll see like the formula that we're actually after. So right now, this is kind of like an intermediate formula. It's not the way I really want to write this out. Because I should write this like in a way that has like the stuff that in order for this to be a useful formula, you have to kind of like rearrange it a little bit. So I want to put all the stuff that's multiplying x together. So here I could put it like this. This looks a lot better. And then I want to put all the stuff with Y together. So what's that? All the stuff with Y. So what's the stuff with Y here? This is the stuff with Y. So it's EB. EF. And then B. And then you can do the same for the bottom one. So what's that? All the stuff with X is this one. So this is, I mean, this is kind of like one of the most tedious parts of the course. I'm just doing it in a lot of detail because matrix multiplication is one of the most important operations, but it is a little bit tedious. Like, there's no denying of that. And then what's this stuff with, I should have used it, oops. Okay, yeah, that doesn't matter. Oops. Okay, here it is. I should have used a different color. Let me see if I can switch it to yellow here. And then the other one, like, let's put like some sort of like blue. No, I don't want to blue. I like this blue. Yeah, maybe this blue is fine. Okay. Exact. So perfect. So right. So just to summarize, because this is like a huge mess of formulas, what I'm saying is like, you can take my word for it. If you start with vector V, run it through A, you get this. And then run it through B, you get this mass, right? That's a mass that's kind of confusing. It is useful to rewrite it so that you see it as number times X plus number times Y, number times X plus number times Y. So these numbers will form the coefficients, the entries of the concatenation matrix, which is what we're going to call now the matrix multiplication. So the idea of the matrix multiplication is that we're going to write this as B times A. Again, why in that way? Because in this notation, this means if you write it like this, that means that you're doing A first and then B, which looks weird, but this is all what this means. Like, so it means literally do A first and then B. And so what I'm saying is that that corresponds to EFGH, because that was a matrix B, and then A, B, C, D, okay? And that corresponds to the four numbers that you see here. EA plus FC, EB plus FD, I should rewrite this one a little bit so that it looks better. FD. And then GA plus HC. And the last entry is GB plus HD. So what I'm saying is that if you had two matrices, two processes with their entries, and you want to know the entry of the matrix that corresponds, that represents the concatenation, these are going to be the entries of that concatenation matrix. Okay. It's just that as it stands, like you would say, how am I supposed to remember this formula, right? It looks like a big mess. So what I will do tomorrow is that I'll give you convenient ways to memorize a formula which involves a dot product. So tomorrow is a good place to start with the dot product, because once we have the dot product, then there is like a very straightforward way to remember this formula. But in the meantime, it is just like a very confusing formula. But I'm just trying to say that this is the entry. What I'm trying to say is that this represents the entries of the matrix that corresponds to doing the matrix A and then the matrix B in this assembly line, in this concatenation. So is that making sense? So again, like this not don't try to memorize the formula as it stands right now. I'll give you tomorrow like a better way to do that. So that's like where I'll start with Wednesday's class, because this will require a little bit of a, it's better to start with this with a fresh mind. So I think it's like a good place to stop. Is that okay? Are there any questions? Well, I will send I will send an announcement today which problems you should check for the quiz on Thursday. The quiz on Thursday will be mostly about finding the matrices, like kind of like the analog of finding the shift matrix or the rotation matrix, things like that. So I'll send you like a list of problems to look at. So it's not an assignment per se, but it will be like the quiz will be based on those problems. So I'll write that in a couple of minutes. Well, the only thing that will be graded at the moment will be the quiz. Yes. I'll send you an announcement what you need to download. Well, the quiz will be in class. I will create that. Let's see. I'll create like a practice with responders, because I think I haven't done it. So I'll do that so that you can practice on that before the quiz. Yeah, exactly. Well, basically that's one way to put it. Yeah, it's like I'll give you like a practice sheet. I'll just tell you which problems to look at from this PDF with the problems list. Yeah.
Professor, could you go back to the mirror part? I have a quick question about that.
Where, sorry?
Okay, actually, I confused a little bit about the mirror part. What elements I should be opposite or reverse? It always should be
Okay.
the X or it always should be the Y?
Oh, sorry. So you're talking about the mirror and the shift part?
The mirror part, actually, because I just confused like when I supposed to,
Oh,
no, I just don't know,
oh,
should I opposite the X or the Y?
oh,
Because the
oh,
situations
oh,
always change.
okay,
So,
okay. The thing of the mirror is that it multiply. You can think about it like this: it multiplies by -1 the second entry. It's better to call it, instead of calling them X or Y, call them first or second entry.
mhm,
So the mirror multiplies by -1 the second entry. So the second entry just happens to be X in this case, right?
mhm.
And that's why it becomes -X.
Okay, so it's always changed in the second
Right.
entry. Okay,
Correct. And the shift is better to say it like without variables. So the shift is, so it changes the first entry with the second entry, right?
yeah, just
So, right.
reverse. Gotcha.
Yes.
Thank you.
So and yeah, but if you say it in terms of X and Y, can be more confusing because sometimes the X or the Y can appear in the first or second entries. Yeah.
Okay, gotcha. Thank you.
Sure. But yeah, like I'll send, right, like what I was saying is that I'll send the review problems for the quiz today. Yeah. Are there any other questions? Yeah, potentially to some, maybe not all, but possibly some. The thing is like the quiz problems will be from the review problems. So I don't want to give all of the answers because of that.
By the way, Professor, I saw the on the campus they're gonna be have the 25 to 50% up to 50 questions sheets, right? PDF.
Yes, yeah.
That is
Uh,
helpful for us to practice.
well, you
'Cause-
don't have to print it, but yeah, that's where like the quiz problems will be based from. Yeah.
Okay.
So
Because I
yeah,
didn't
so
see answers to check. So
because not everyone has a textbook, so I don't want to refer to questions on the textbook directly.
okay.
Yeah. So I'll say to study certain problems from that PDF guide. Yeah.
Will there have any answers for us? For
Well, that's kind of what I was saying. It will. Yeah. I mean, depending on the type of the problem, yes. Not all because but just to some. It's just that those will be the. I prefer to do it where like the problems on the quiz will be just copy pasted from that PDF. So if giving the problems because of like the full solution would seem too much. But yeah, I could give you some potential answers to them. Yeah.
okay. Sure.
Yeah. Okay. Are there any other questions? It's some modules. I can share it here. Yeah, I don't know if you saw it. I can share the screen. Oops. Sure. It is here. Anyone else? Okay, I'll work on that announcement and then send it to you in a couple of minutes if that sounds good. Then. Yeah, I'll also open the office like if someone wants, like I'll still have the office hours at 10, so I'll just close this meeting to save the video and then but I'll reopen it at 10 for in case someone wants to show up for and ask me something else. Okay, I'll see you tomorrow otherwise. Good.
Thank you, Professor.
Bye bye.
Thank you.
You too. Bye.